Okay, so now we're on to part two. Okay, we're starting with question number 5. Which is true about a 95% confidence interval based on a given sample? Okay, so the interval contains 95% of the population. This of the population prepositional phrase, when you're talking about confidence intervals and p-values and stuff like that, is usually a dead giveaway that that's wrong. Okay, the results from 95% of all samples will lie in the interval. Remember, a confidence interval is based upon our confidence that the actual population is inside the interval. Okay, all right. It doesn't say how much of the population is in there. It's just the center, the mean of the population, and so uh, tons of samples are going to lie outside of the interval, and so it's not 95% of all samples. Um, the interval is narrower than a 98% confidence interval would be. Yeah, absolutely, right? If you want to be 95% sure that you have the center, you're going to go like this. But remember, this is your confidence that the true population parameter is in there. And so if you go out to 98% confidence, remember you need a much wider net to potentially catch it. And so number 3 is the only one that makes sense. Okay, let's move up, right? So we can continue to focus on what's important. Double blinding in experiments is important so that, right, um, the evaluators do not know which treatment group the participants are in. Yeah, so this is important, right? So for double blinding, right, the evaluators don't know who is in the treatment group, so they can't bias the response. The participants don't know which treatment group they are in, so they can't bias the response. And this is the double blinding part, so that's really important. And 3, no one knows which treatment group any of the participants are getting. Okay, this would be totally bad. All right, if no one knows, usually there's a head researcher or a lead investigator or something that knows, based upon non-personally identifiable information, which group the participants are in, so that they can actually compare the results. If nobody knows, then how are you going to make any sort of a conclusion at the end? So 3 is just crumbs, right? So 1 and 2 are correct, and so the correct answer here is 2. And I really like the answers 1 and 2 because these are basically the definition of double blinding, right? You have these two components. All right, so 7, let's go ahead and scroll up. All right, so not wanting to risk poor sales for a new soda flavor, a company decides to run one or more tests on potential customers, this time requiring a higher approval rating than they had for earlier tests. So they've done some sort of a pilot, okay, on the potential new soda flavor, and this time they really want a higher approval rating than they had for earlier tests. Okay, so they weren't real happy with earlier results. This higher standard of proof will increase, okay? Now we have to think about what we're doing here. All right, so when I have these type 1, type 2 errors, I always find that the chart is super duper helpful. So usually what I do is I write H not true, I write H not false, I write reject, right? I write fail to reject. Remember, this is a type 1 error. This is actually a correct assumption. This is a correct assumption, and this is a type 2 error. Okay? And so if we are looking at this, we want to make sure that we have a higher approval rating than we had for earlier tests. If you create a higher standard, right? A higher standard. What I think they're saying here with this higher standard is increasing alpha, right? So as you increase okay, so what they mean by this higher standard of proof is you are going to take alpha and make it smaller. So you're going to have a smaller alpha. For a higher standard of proof, you have a smaller alpha. Well, with a smaller alpha, right, the chances of having your p-value be less than alpha go down, right? Because as alpha goes down, the p-value actually has to get smaller and smaller. And so what will probably end up happening is the p-value now is actually going to be greater than alpha. And if the p-value is greater than alpha, then we fail to reject, right? If the p-value is greater than alpha, we're going to fail to reject. Well, if you fail to reject, the only type of error you can make is a type 2 error. And so if we're making a type 2 error, then we are only going to answer A. Alright? Now, type 1 error and power are related because they're related to the alpha here. So you could have 1 and 3 being together, right? 1 and 3. This is a possibility, but not here, right? Because we want a higher standard, and that gives you a smaller alpha. Okay? So let's see if we can get 8 and 9 done and sort of finish up this page. Okay? An elementary school principal wants to know the mean number of children and families whose children attend this school. He checks all the families using the school's registration records, and we use a computer to create a 95% confidence interval based on a t-distribution. This procedure is not appropriate. Why? Okay, he actually checked all the families. If you check all of the families, you know exactly what your mean value is for your population, okay? So the entire population of families was gathered, so there's no reason to do an inference, all right? I mean, when you do all the families, there is no reason to do an inference, and so A is the only correct answer here. Yeah, I mean, all of these other ones are yeah, they're just crap, okay? So don't worry about them. All right. 9. Of the following, which is not a critical part of good experimental design? And here, this is going to be A, the random selection of subjects. Remember, it's really hard to randomly select subjects, so what we do is we want to make sure that we randomly assign the subjects to the treatments, and this allows us to get rid of any confounding or lurking variables, or make sure that each one is representative. And so to get a representative sample, we do random assignment, not random selection. Okay? Replication is really important because we only have random assignment. We can't actually select subjects. All of these are not important because random selection is not important. Okay? And then control of known sources of variability. Well, this is an important part of the process too, right? Now, is it A or C? Which is the best answer? Well, we would like to randomly select subjects. Okay, so C is better than A, and so here, if you want the not critical part, the random selection is the not critical part. And so while you might be tempted to say all of these are important is also not critical, well, replication and control and random assignment are all really important. So you can't say all of these are unimportant, sort of the inverse, because some are. So you can't throw the baby out with the bathwater here. All right, so this concludes part 2. Okay, we got the 9 questions on just another page, and so we're just going to keep cranking into part 3.